This is an animation of a particle collision in the Large Hadron Collider, as seen and reconstructed by our particle detectors. Now, what we usually say when showing these is something like, by carefully analyzing the particles that come out of the collision, scientists try to understand what happened there in the center. But how do we do that exactly? These are plots that were shown during the seminar at which Atlas and CMS announced the discovery of a new particle in 2012. And we were saying something like, we have observed a new
boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviation.
We observe an excess of 5.0 sigma in this region.
Everybody was getting excited about the bump, the peak in the plot. There was the sign of this new particle, the Higgs boson. But what are these plots really telling us? What's the link between such plots and the particle collisions? In this mini-series, I'll walk you through the Higgs boson discovery. I'll try to explain how we figure out what happened in the particle collision by looking at what comes out, and why the evidence for discovery is a plot with a little peak in it. This is the Higgs boson discovery explained. The first thing we need to make clear is that the hunt for the Higgs was not literally a hunt. A particle like the Higgs boson is not something that you can find by going somewhere to look for it. Its lifetime is so short, it's almost zero, so even if one got produced somewhere, it would immediately decay into other particles. So basically, it cannot be found in nature. So the only way to check whether such particles exist and study their properties is to make them for ourselves in the lab. The main ingredient that we need to make particles is energy. So let's first ask ourselves, what is energy really? Well, first of all, energy is not something that I can sort of bring in a bucket and pour into a particle creation device. In fact, energy by itself doesn't really make sense. Energy is a property of things, like velocity, for example. An object can have velocity. It's always the velocity of something. And it's the same thing with energy. So energy comes in various forms. For example, objects that move have what we call kinetic energy, from the Greek word kinesis, meaning motion. But we also know from Einstein that every object that has mass has an energy corresponding to this mass, equal to that mass, multiplied by the speed of light, squared. So mass is in a sense equivalent to energy. It's a form of energy that objects possess. Different forms of energy can transform into one another in various processes just as long as the total energy is conserved. For example, if I take an object and toss it in... I need an object for that. Thank you. If I take an object and toss it in the air, I start by giving it kinetic energy, then it changes into potential energy as it goes up. At the highest point, it's only potential energy, there's no motion anymore, and then the object falls down, back into my hand. It recovers the kinetic energy, which then in turn transforms into heat as it impacts the palm of my hand. So we have a flow from kinetic energy, potential energy, back into kinetic energy, and then into heat, which, by the way, is also kinetic energy. So when we collide particles, two types of energy play a part in this story. It's kinetic energy and mass. So in particle collisions, kinetic energy can transform into mass. We can take two lightweight particles, put a lot of kinetic energy into them, collide them, and have them create one particle that's very massive. And for this, you need a particle collider, like this large one here. What happens here is we have two vacuum pipes inside these magnets, and in the vacuum pipes, we have two beams of protons going in opposite directions. And we accelerate these protons, and as we accelerate them, we're essentially pouring energy into these protons. The protons themselves become the buckets in which we carry the energy to the collision point. Now, in the collision point, the two beams get smashed together, and the energy in the protons, the sum of the energy in this beam and this beam, becomes available for the creation of mass. Now, there's a small subtlety here. Since protons are actually made of quarks and gluons, what physically collides is not the whole proton, but the tiny constituents of it. So only a fraction of the energy of the proton becomes available in the collision. So when we finally collide these particles, what's going to happen? Well, here's the thing, something different every time. Because experiments like these, it's not like an experiment where you just take an object, throw it in some distance, at some angle, see how far it goes, or you, I don't know, take some material, measure its resistance in certain conditions. In these experiments, what happens is particles arrive in there through a beam pipe that's currently not in place because it's been taken out to be upgraded. They come through there, from there, and they go into the center of the detector where they collide with the beam coming from the other side. What happens in this collision? Well, what happens there is governed by quantum mechanics. There's a lot of very complicated physics that allows us to predict what can happen and with what probability. But that's really all we can predict, not what will happen, but what can happen and what's the probability of that happening. And at the end of the day, nature will just pick one possibility every time we collide particles. So this is step one, producing the Higgs boson. Now let me close by giving you some numbers. The energy of the protons colliding in the LHC is about 100 times bigger than the mass of the Higgs boson. And yet, we only produce a Higgs boson once in about 1 billion collisions. On the other hand, we have collisions 40 million times a second. What happens 40 million times a second? About 30 protons smash into each other. So 30 times 40 million, that's about 1 billion collisions per second overall. So in the end, this gives us one Higgs boson about every second. But how can we see them? How do we know that we're producing them? Well, we'll continue the story in the second episode called Detect.